Good evening, once again, and welcome. I'm Liam Kennedy, your host for tonight's episode of Look Up Tonight. This is the cable show of the Orange County Astronomers. We're one of the largest amateur astronomy clubs in the country and invite everyone to watch our show and learn what our club is all about and how you can learn about this wonderful hobby. Orange County Astronomers has activities for all levels of amateur. Many new amateurs take part in our Beginners Astronomy program at the Centennial Heritage Museum in Santa Ana. We also hold monthly star parties locally at Black Star Canyon, as well as our large desert site outside of Anza, 30 miles east of Temecula. Another very popular activity is our monthly club meeting, which is open to the general public. Our most recent speaker at the March meeting, Dr. Luisa Rebull from Caltech, a project scientist with the Spitzer Space Telescope, presented the latest observations and discoveries made with that great observatory. The Spitzer Space Telescope was launched last August into orbit. It observes the universe in infrared light, while the Hubble Space Telescope that everyone's heard so much about observes mostly in visible light. As you'll find out, the universe looks very different through infrared eyes. Here is Dr. Rebull.
So, I am in fact going to be talking about the first results from the Spitzer Space Telescope. First, I'll talk a little bit about an introduction to infrared. I'll talk a little bit about Spitzer history, and then we'll talk a little bit about the very newest Spitzer results. I have images and spectra. And then I'll tell you a little bit about why the pictures are more than just pretty pictures, what makes them interesting scientifically. And I'll even show you how you can access the data too, and then I'll sum up. As you may or may not know, Spitzer is NASA's fourth and final great observatory. The other observatories in the sequence were Compton Gamma Ray Observatory, that has since re-entered the atmosphere, Chandra X-ray Observatory, which is currently flying, the Hubble Space Telescope, of course, and now the Spitzer Space Telescope. So that's one way of looking at the electromagnetic spectrum. Here we have visible here, but you probably know there's lots of light beyond the visible. There's ultraviolet, X-rays, gamma rays, infrared, and radio somewhere out there. This is another way of looking at the electromagnetic spectrum. This is galaxies, the same galaxy at many different wavelengths. So here's what it looks like in X-rays. Chandra is an example of an observatory that observes in X-rays. Ultraviolet, GALEX, you might have heard, is a mission. Also HST does some ultraviolet work. Visible is, of course, HST. Near IR is 2MASS. You might have heard of that survey. That was a ground-based near-infrared survey. Spitzer also overlaps a little bit in the near-infrared regime. And, of course, the far-infrared, which is also what Spitzer observes. So this is a lot of information, so let me go through it a little bit here. This is the wavelength of the light. So 2 nanometers. A nanometer is a billionth of a meter. So this is a little tiny wavelength, but look at the temperatures of the stuff that's emitting in X-rays. That's 1,000,000 Kelvin. So that's little tiny wavelength, really big temperature, okay? You get down to ultraviolet, you have 200 nanometers about, and you're looking at about 14,500 degrees. Here you have in the visible light, about 500 nanometers, which is about 5,800 Kelvin. Down in the near infrared, you're looking at about a 1,600 nanometer wavelength, about 1,800 Kelvin. And when you get out to the far infrared, it's about 100,000 nanometers, down to only about 30 degrees above absolute zero. So the kinds of things you're looking at in these regimes are black holes for X-rays, hot young stars in ultraviolet, run-of-the-mill stars in HST, in visible light. And near infrared has very cool stars, which are usually the old ones. And in far infrared, you're looking at cool dust heated by hot stars. So this is another way of looking at the electromagnetic spectrum. This is how people in my office look at the electromagnetic spectrum. Okay, so the world really does look very different in the infrared. Here we have a cute little dog in visible and in infrared. So there's two things you can notice about this. One is that it's a false color image. I've taken the wavelengths of infrared light and translated them into colors that we can see. And the other thing to notice is that those colors correspond to temperature. So because he's a fluffy little dog, the outside edges of his fluffy fur around his head there are actually pretty cool, but his ears are warm, his face is quite warm, but because he's a healthy dog, his nose is cold. Okay? So that the main thing here is that the hot things glow in the infrared. So here we have just a regular run-of-the-mill bathroom faucet running water. So which one of those is the hot water and which one is the cold? Okay, who raise your hand. Who thinks the top one is the hot water? Who thinks it's the cold water? Yeah, you guys got it. The top one's the cold water and the bottom is the hot water. You can even see the base of the faucet is cold here and hot there. So infrared can also reveal things that are hidden in visible light. Here's a hairdryer. Try to imagine what you think this might look like in the infrared. I can tell you it's on. I love the turbulence in that. I just think that's really cool. There's lots and lots of really neat infrared world photos online at the Spitzer website. I've linked it into my website that I set up for you guys. If you've ever wondered what an alligator looks like in the infrared, this is where you go. They've done all sorts of really interesting things. They went to the zoo with the infrared camera, but they've also got some more mundane things like a frozen burrito just out of the microwave. So lots of neat things to look at online. So I just have a couple more infrared world photos here. One of the neat things about infrared is that it can see through some things that are opaque in visible light. So this is just a run-of-the-mill garbage bag, what you might put your yard waste in, but yet you can see right through it in the infrared. Some things transparent in visible light are opaque in infrared. This is just a glass door in my living room, and it's really hard to see me in the infrared. It turns out you already know this. You know this intuitively. Because when you park your car in the sun in August, the visible light comes through your windshield, warms up your car, and the infrared stays in the car. So this is why you have to drive like this when you get in the car, okay? So here's one more view of the world in infrared. Now we're starting to get closer to the astronomical concepts we'll be talking about tonight. This is frozen peas, believe it or not, in liquid nitrogen. So here's something called a dewar. It's just basically a fancy thermos with liquid nitrogen in it. And there's no peas in there yet. The infrared camera just sees that as dang cold, okay? It can't even tell that that's 77 degrees Kelvin. It just registers it as really cold. Here, I've put the peas in the liquid nitrogen. And here, the peas, even though they're cold, they show up as bright in the infrared. So that's kind of the point, because in space, many objects are very, very cold, but they're very bright compared to how cold space is. So this is the kind of thing that we're going to be working with when we look in space in the infrared. So now let's actually start looking at space in the infrared. This is good old familiar Orion in visible light and in infrared. How much you miss if you just stick to the visible light. The Orion star-forming region in the sword there is clearly doing something very interesting in the infrared. Even the belt's doing something interesting. You can look here and see a circle. It's probably an old supernova that's gone off there, pushing the gas and dust around. And here there's another star-forming region here that you might not even know was there. So Spitzer is really opening the infrared window on the universe for us. So let me digress just a minute, spend some time on infrared astronomer units. Wavelengths in astronomy are really commonly expressed in microns, which is a millionth of a meter. It's usually abbreviated mu-m, but if you don't have a mu handy, it's just um, okay? And since mu's don't always translate real well in PowerPoint, frequently you'll see me using the mu. So 5,000 angstroms is about 500 nanometers, is about half a micron. That's visible light. That's the kinds of thing that you're used to encountering. Near infrared is about 1 to 5 microns. That's about the size of smoke particles or pollution particles. And I know that when you're breathing on a really bad day, it feels larger than this. But truly, these are about the size of smoke particles. Mid-infrared is about 5 to 30 microns, which is about the size of a hair. 30 to 350 microns is the far infrared. That's about the size of a table salt grain. Think about that. That's a really big photon compared to what you usually encounter, okay? And if you really want to sling the jargon around, you can use Janskys rather than magnitudes. Because that's just it, because the people that founded infrared astronomy were coming at it from the radio, and that they carried their units with them from the radio. So there's two key science questions for Spitzer. One is, how do stars and planetary systems form and evolve? And the other is, what did the early universe look like? So the kinds of observations that we're able to do include looking at the dusty universe, because the hot stars heat the gas and dust around them, heating up the dust so it glows in the infrared. We look at the cold universe. A lot of the light, the IR light that comes to us, is coming from pretty cold stuff that's out there. We can also look at the distant universe, including things like the ultra-deep field, because most of the light that comes to us from distant galaxies is in the infrared. Another way of thinking about this is it's the old, the cold, and the dirty. So why do we need to go to space to do this? Space is cold. To paraphrase Douglas Adams, it is mind-bogglingly cold. You wouldn't believe how cold it really is. The Earth, it turns out, is actually quite warm, as is the atmosphere. So by simply getting out of the atmosphere, we gain a lot in sensitivity. The other thing is that the atmosphere actually absorbs most of the infrared light. So here we have opacity as a function of wavelength. Basically, it's saying how much of the light in that regime comes down to the ground. So here's visible light, makes it all the way down to the ground. There's holes in the near infrared if you're lucky and it's dry and you get up to a high mountain, you'll be able to see some of those. But then Spitzer really observes in this regime in here where it has no hope of making it down to the ground. The radio out here makes it all the way down to the ground, of course. So a little bit of history of Spitzer. Spitzer, at least in concept, has been around since the late 1970s. There was a really very successful satellite called IRAS, which was launched in 1983. In terms of bang for the buck, it's hard to beat IRAS. In terms of scientific revolutions or revelations per unit time that it came up with, it's really one of the most successful, if not the most successful, NASA spacecraft. So we knew from IRAS that we needed to follow it up with a pointed observatory such as Spitzer. The 3 Spitzer instruments were actually selected in 1984. The project was nearly canceled several times in the era of faster, better, cheaper. We had to go through a major descope in the early 90s, which I'll talk more about in a moment. We had a successful launch in August, and nominal operations began in the beginning of December. We got a new name and a big press conference on December 18th, and we're expecting to have a longer than 5-year cryogenic mission. What do I mean by cryogenic mission? Well, because we have to keep our telescope cold, our lifeblood is really our cryogen. Because we're looking at very cold things, we have to make sure that our telescope is colder than the stuff we're looking at. So the old design, the one that IRAS flew with, is here, where you see the whole telescope is inside a bath of cryogen. But in the early 90s, some really, truly brilliant engineers got together and thought of ways to make this mission work, but still cost less. So what they did here was they put the telescope outside of the cryogen. That means that we were launched warm and we cooled down on orbit. So that means when we launched in August, our telescope was a temperature of an August night in Florida. And now we're down at 5.5 Kelvin. So it really is an amazing system, the way that they figured out how to make this thing cool off. One of the things that really enabled this was that we're in a solar orbit, not in an Earth orbit. Simply by getting away from the Earth, we're able to cool down very efficiently. So just look at the comparisons of some of the numbers here. You can just look at the spacecraft, see how much smaller it is. You can tell that it's going to take a lot smaller rocket to launch it. When we actually launched, a lot of people were very relieved that it actually worked, and it actually worked better than a lot of people thought that it would. So you're going to see the same design again in future NASA missions. Because it works like a charm. So Spitzer does in fact orbit the sun, and it sort of moves away from us steadily. By the time you run out of cryogen, it'll be about 0.6 AU away from us. And as I said, by moving away from the Earth, it has a better thermal environment. We can actually passively cool as we do. And it turns out that observatories that are in Earth orbit actually spend a considerable amount of time simply trying not to look at the Earth. By getting away from the Earth, we are a very efficient observatory. We don't have to worry about accidentally looking at the Earth. We can spend most of our time observing astronomical objects. And also, some of you might know about the Van Allen belts around the Earth. These are actually very harmful to spacecraft. You might have heard that Chandra actually accidentally damaged itself by having its detectors in an unfortunate configuration when it went through a radiation belt and damaged one of its detectors. We're well outside the radiation belts. We don't need to worry about that either. So Spitzer is in fact more than 5 million miles away now. It's in the direction of Aries, and it lags the Earth by about 7.5 days. So our life's blood of helium, we only use about 1 ounce a day because we're cooling passively very efficiently. This is a very technical slide, but it does show you, here's the solar panels, here's the shiny part of the spacecraft. The side that always faces the sun is, of course, the solar panels. Behind the solar panels, the telescope here itself is actually shiny to help reflect any heat away, and then the back of it is black, radiating out into space. So the other thing that's interesting to note on here is it's only an 85 centimeter f12 telescope, but it's made entirely out of beryllium. Okay, this is a substance that I'm told, I didn't actually see the primary mirror, but I'm told that the photographer had to get into a very special angle in order for it to reflect in the visible light like this. Because of course this thing is designed to reflect infrared light, not necessarily visible. So apparently most of it looks like this matte, flat black, unless you get in exactly the right angle. So it's a pretty nifty thing. The entire thing is made out of beryllium so that it cools down evenly. We have 3 instruments on Spitzer. One is the infrared spectrograph, or IRS. It has 4 modules, 1, 2, 3, and 4 there. They have different wavelength coverages and resolution, but they cover between 5 and 40 microns. There's MIPS, which is the multiband imaging photometer for Spitzer. That's the one I work for. It's our long wavelength imager. It's got the only moving part on Spitzer. There are 3 cameras in there. They cover between 20 and 180 microns. And then there's IRAC here. This IRAC is our shorter wavelength imager. It's the infrared array camera. There are 4 infrared array imager. It's got 4 cameras in there covering between 3 and 10 microns. I put this in because I just think it's a cool picture. This is Spitzer before it got its solar panels while it was at Lockheed Martin. It's actually in a bay here that was used to assemble Hubble. That's why we look kind of small in the bay, because we're actually much smaller than Hubble. So this is a cross-section of the observatory. Here's the beryllium telescope there. There's where the instruments live. Here's where the cryogen lives. Here's all the business part of the spacecraft, where our antenna is, our batteries. We have nitrogen to help thrust around to point the spacecraft. Our star trackers down here, and the solar panels are here. So you see where we kink in right there? Right here? That's where the telescope is, right in there. And the cryogen lives down there. Okay, so I am at heart a NASA junkie. So I think pictures like this are cool. This is assembling a rocket down at Cape Canaveral Air Force Station. You see it's got our Certif logo on it there and everything. So this is the second stage of the Delta II going up. I actually had to, I could talk just an hour on all the pictures that they took of assembling the rocket. I thought it was cool. There's Spitzer going up in this payload canister being hoisted up to the top. And there's the fairing going into place. The fairing is the top of the rocket, the thing that makes the top of the rocket look like a rocket. Okay, so there's the other half of it going, closing in place around Spitzer. The really sharp-eyed among you will note that this says April 2003, and yet I said earlier we launched in August. Here's Spitzer coming down again. So what actually happened is that we were all set to be the first launch since Columbia. So NASA was a little nervous. And it turns out we have solid rocket boosters strapped around the main rocket. I'll show you pictures of that in a moment. And they found cracks in some of the insulation in those solid rocket boosters. And they were a little nervous. They wanted to chase down some paperwork, maybe do some more testing. They were a little nervous. We didn't have to go in April. We really wanted to go, but we didn't have to go. The Mars missions, however, had to go in June and July. So Spirit took our rocket. When they assemble these rockets, there's only one way it's leaving the pad, and that's up. So they painted a Mars logo over our Spitzer logo, our Certif logo, and they took our rocket. Something that every time we run into those MER people on lab, we remind them about. So this is rocket number 2 going into place with the Certif logo on it, setting up in July 2003. And here are those infamous solid rocket boosters. We actually have 9 strapped around. It's kind of cool. They light 6 on the ground, and then in the air they light the last 3. This is all ready for the second stage, and there's Spitzer going back up again. Now we're finally ready for launch. You can see the umbilicals attached in there. There we go. So this is pretty close to what I actually saw when I went down there. It turns out that Cape Canaveral is a lot larger than you might think it is, and the launch pads for the manned missions are actually a long way away from the unmanned launch pads. And the special place that they let mission people go are really close to the manned launch pads, but not so close to the unmanned launch pads. So the best place to see the unmanned launches is from a place called Jetty Point, which is a public park. It's got a lot of fishermen who spend the night, a lot of campers. So there's this long pier that goes way out here, and the launch pads are in there, obviously. I was way out on the launch pad with about 200 other astronomers and a couple of annoyed fishermen screaming, "Go, baby, go!" Let me give you our launch, but in infrared. It's going to go through a cloud bank about now. So the rest of it, you sort of get to watch the exhaust plume disperse. So about 120 days of hard work later, we got a new name. The name was chosen from more than 7,000 entries submitted to NASA. It was named for Professor Lyman Spitzer, who was a professor at Princeton University. And he did a lot of really interesting things. He was a really amazingly brilliant man. But the thing that I think is the most interesting was that in 1946, Dr. Spitzer suggested putting a telescope in space. Think about this. In 1946, the only things that we had as a world population that could legitimately be called rockets were German V2s. Okay? And yet this man had the vision to say, let's put a telescope in space. Let's get it up above the atmosphere. We won't have to worry about the seeing. We won't have to worry about these other things. Let's get it up above the atmosphere. I think at first they probably thought he was nuts. But he was very persistent. He actually got a couple of smaller telescopes up there first, and he turned out to have been a primary force behind Hubble, lobbying Congress to make sure the funding went through. And when he died, he was actually working on Hubble observations. Another reason why this is a good name choice is that Dr. Spitzer really did found the science of the study of the interstellar medium. That's the stuff between the stars, and that's what Spitzer really sees a lot of. So this is an optical image of IC 1396, which is in Cepheus. It's about 3,000 light years away. This image is about a moon across. It's part of a larger complex, which is 10 full moons across, but this image is only about a moon across. So if my PowerPoint doesn't fail me, this is going to fade into IRAC several times. Okay? So the thing to notice is that you're seeing right through that dust to see all the stars that are in there. Let me do that again. There we go, oohs and ahs, there we go. You can see why we wanted to call this either the running man or the flying dragon, something like that. So here's another view of it. What I was just showing you, the pinker image was IRAC data. This is MIPS, the longer wavelength. This is a combination of the two. And they've chosen the colors just right so that all the green stuff is molecular hydrogen, and the brown stuff is something called polycyclic aromatic hydrocarbons, which is usually just abbreviated PAHs. These are just rings of carbon. You can find them. It's the grunge you find on your grill. Okay? Little tiny particles like that all over space. Lots and lots of rings of carbon. And so that's what all that brown stuff is. Okay? So in order to tell you why this is an astrophysically interesting image, let me give you a little bit of background first. This is probably how the sun formed. This is our best understanding of how low-mass stars like our sun form. It starts in a big, dark cloud with little dense cores in it. One of them starts to gravitationally collapse. Then in the center, you've got this young object in there, and just because of the way the physics works, it doesn't fall straight in. It falls into a disk first, and then it falls into the star. So you have like a record or a compact disk of stuff around the star. And for reasons we don't entirely understand, you get jets coming off the star. So you note here that you're inside this cocoon of matter here. Eventually, it disperses that cocoon, and you're left with a thinner disk, but still a disk, and the jets. And then eventually the jets turn off, the disk thins out a little bit, and you get a little planetary debris disk around that protostar. And then eventually you get a genuine, bona fide, hydrogen-burning, mortgage-paying adult star. Okay? with a planetary system around it there. So look at the scales here. This is a huge cloud. It's 200,000 AU, and AU is the distance between the Earth and the Sun. This is just zooming in on one of the clumps, okay? So by the time you get down to a solar system, you've gone from something that's 10,000 AU down to 50 AU. So things are collapsing in, okay? This is just a more technical way of looking at that. This is basically energy or brightness as a function of wavelength. This is just the central object, but you see most of the energy is coming out in the infrared. It's coming out from that cocoon of matter around the star. Here you get a little bit of infrared excess from the disk, and here there's a little tiny bit of infrared from the disk, the remnant disk that's around it there. Okay, so now let's look at that data from IC 1396. Here you've got the visible light that's all dark, the IRAC where you're seeing through, and the MIPS where you're looking in the really long wavelengths. Are there questions? I should have said, feel free to raise your hand, ask questions. Don't heckle, but yeah. So the way that this works is you have a really bright star over here, and it's actually putting out so much energy that it's pushing the gas and dust around. You can almost see it boiling off with that red glow on the edge there. Okay? So it's pushing the gas and dust around over this way. You can also see there's a little hole in there. That's because there's a little couple of baby stars in there that are pretty bright, and they're pushing the gas and dust around on their own in there. So that hole you can see in all three of the images. Now here you see something that's very bright. In IRAC, the middle, the near IR, the near to mid IR images, you've got two objects that are sort of comparable brightness and two more that you don't even see over here. And then over in MIPS, the longest wavelength, you've lost three of them. You only have that one, which is one of those. So what this is telling us is that this guy has already blown off its cocoon of matter. It's probably on the front edge of this cloud. But this one, it's probably very similar to its friend over here, but its friend is more deeply embedded in the cloud. So remember the cocoon over here? That's what we're looking at. That's exactly the kind of thing we're looking at, because it's embedded in the gas and dust. Now these guys too are also embedded, but that one's got a lot of gas and dust around it in order for it to be bright at 24 microns like that. So what this is telling us is we have a family here of stars at slightly different ages. Okay, because the guy in front is probably the oldest, and the guy that's most deeply embedded is probably the youngest of those group. If you look, you can actually probably find other stars with similar patterns. Stars that are going to be comparably bright in IRAC, but bright in MIPS and probably gone in the visible light. So let's see if I remembered everything to tell you about this. This is hopefully everything I just told you about this. The name of that bright star that's pushing the gas and dust around is HD 206297. And these are the names of the two little guys in the hole in the head. And this is everything that I was just saying. This is just a cartoon to show you how the gas and dust push around to leave sort of the head like that. And this is a picture from Hubble that might give you an idea of what one of these disks might look like. It's an edge-on disk in this picture. Now, who can think of where else in the universe you might have seen these processes in action? I'll give you a hint. It's the most popular image on the Hubble website. Eagle Nebula, exactly. Here, the really bright star is up here, and it's pushing the gas and dust around like this. Now, this image is only, remember the IC 1396 image was about a moon across? This is only 1.2 arc minutes across. So this is a much different resolution. This is exactly what keeps our public affairs people up at night in cold sweats. Because you guys are so used to the Hubble images, we're so worried you're not going to like our images. So, because as the phrase goes, an educated consumer is our best customer, let me tell you a little bit about the differences between Spitzer and Hubble. Of course, Spitzer observes in much longer wavelengths and is generally seeing cooler things and through dust, which Hubble can't see through at all. Hubble is, of course, in Earth orbit. Spitzer's in solar orbit. So that means that politics notwithstanding, there is no servicing mission possible to Spitzer. When we run out of cryogen, that's it. Okay? For comparison, the Chandra Observatory does about 3 observations per day. HST can do about 10 observations per day, but Spitzer can do about 55 observations per day. Part of that is that there's more infrared photons around. Some of that is because Spitzer's really incredibly sensitive. Spitzer is really, really good at covering large areas of sky. Hubble is really good at really tiny fields of view, but Spitzer is really good at covering large areas of sky. Spitzer is really phenomenally sensitive. It's more sensitive than any other infrared telescope to date, but the telescope's actually fairly small. It's only 85 centimeters, so the resolution matters. Hubble has much higher spatial resolution, and part of that is because it's working with smaller wavelengths of light. So just a little bit of an aside on resolution. Here are those galaxies at many wavelengths again. But what you see here, this is the original visible light image, but in order to fairly compare it to what Spitzer sees, you have to smooth it out so it's the same resolution. So here, all of those galaxies are at the same spatial resolution, so then it's fair to compare the different wavelengths. So here's another important implication of our small telescope and large wavelengths, is that we're actually diffraction limited. Every telescope in space produces images limited really only by the physics of light itself. You guys on Earth here, what you see is smeared out due to the atmosphere, but when you get up above it, you don't have to worry about that smearing. You're really just limited by the physics of light. So what happens is, when you have a long wavelength and a small telescope, you actually start to see they're called airy rings. You start to see the actual, in essence, the physics of light. So you only notice this if you sample the output from the telescope finely enough. So it turns out that NICMOS and HST has airy rings, but Spitzer does too. This is a Spitzer point spread function. So in reality, what this means is that Spitzer can detect galaxies to very great distances because it's very, very sensitive, but it can't tell you what shape these galaxies are. As far as it's concerned, they're just indistinguishable from stars. So you can see that there's a ring around there. And so if you actually look closely at that MIPS image from before, you can see the rings around the bright sources. Those aren't real in the sense that there's not really rings of stuff around each of those objects. That's just a result of the fact that we have long wavelengths in a small telescope. But if you're really good, you can measure that point spread function very, very carefully and then subtract it out of the images, and that's what they've done here. This is images of Fomalhaut, which is the 18th brightest star in the sky. It's only 25 light years away. And what you're looking at here is a dust disk around Fomalhaut. So remember that cartoon from before? That's the kind of thing we're looking at. We knew that this object had a dust disk from observations with IRAS. IRAS couldn't resolve it. Remember that mission back in 1983. It couldn't resolve the dust disk, but it saw that it was very, very bright in the infrared. So people have been looking at it since then. This includes observations from the JCMT at 450 microns here. But what we have here are the Spitzer data here. Here's at 24 microns, and this is 70 microns. The best way that I've heard of to describe this is sort of like a jelly donut. The 24 microns is the jelly, and the 70 is the cakey part of the donut, okay? You're looking at it edge on, so this is a huge dust disk. This is about 5 times the diameter of our solar system. This is huge. And so the 70 micron is looking at the dust around the outer edges, sort of the equivalent of a Kuiper belt. And this is looking at the inner parts of this system and into about 10 AU away from the central star. So the other interesting thing that you're seeing here is that the 70 micron is not evenly bright on both sides. There's more stuff here. So what that probably means is that there's more dust down there. So that means that either there's a planet forming, because the planets can shepherd the dust, just like the moon's and Saturn's rings shepherd the rings. You can actually have that effect. Or maybe there was a recent collision between comets there, creating extra dust. Let's see if I remembered everything right. It's, the dust ring, here's the specs on the dust ring. It's 370 AU, 34 billion miles, which is 5 times larger than our solar system. And I believe I said everything. Oh, one more thing. You guys know about zodiacal dust, right? Nod, yes, no, zodiacal dust. Okay, it turns out zodiacal dust is really important. It's basically our own remnant dust disk. And it turns out that's actually a unit. When you look at other stars, astronomers talk about this star has so many zodies of dust around it. Yes, zodies. So when you're looking in, so this is basically looking at the analogous zodiacal light around Fomalhaut. Okay, so comets. This we can, of course, observe moving targets too. This is periodic comet Schwarzmann-Wachmann 1. It is in a nearly circular orbit just outside that of Jupiter. It's got a period of about 15 years. It was about 6 AU away when we took this image. This turns out to be kind of an interesting object. It's Centaur, which is sort of not really an asteroid, not really a comet either. When I think of asteroids, I think of rocks. Okay? When I think of comets, I think of dirty ice balls. Centaurs are sort of in between. They look like asteroids, but they have coma. They heat up and outgas, just like comets do. So they're kind of interesting things. They live between Jupiter and Neptune, and right now we don't know very many, but I have a suspicion that Spitzer's going to find more for us. This is a MIPS 24 micron image, and the core of it, the nucleus, is actually too small to be resolved by Spitzer. So all of this is outgassing from the object. And those are two little asteroids that we caught just by chance in there. Well, this is one of the first images that we took, so these were some of the first images of asteroids, of the smallest asteroids at that point yet imaged in infrared in these wavelengths. So let's see, what else can I tell you about this object? This is a particularly interesting object because it undergoes periodic brightnesses, brightening and dimming. What they think is going on is that you've got a hard crust, a hard dark crust, and the sunlight hits it, warms up the gas inside, and eventually the gas pressure builds up so much that it pops through the crust, and that's what causes it to brighten. Did I remember everything? Let's see. Here's the velocities of the stuff coming off when it ruptures, 200 meters per second. It's coming off at a pretty good clip. The comet nucleus diameter is only about 18 miles, and it's too small to be resolved. These are the names of those two little asteroids that we caught by chance, and they're only about 1.4 and 3 kilometers. So they were at that time, they were the smallest asteroids yet measured, although since then we've caught more. So this is another protostar. This is on the left, my left, your left. There's optical, and there's Spitzer Iraq. Remember that cartoon with the jets coming off? That's what's going on here. You've got jets coming off. It's totally invisible in the optical, really, and it just pops out really dramatically with Iraq. This is pretty much everything I was telling you before. Sometimes, basically, they were saying that this is particularly interesting because the sun might have gone through a similar phase earlier. Now, I've been showing you a lot of images. This is the first spectrum that I've shown you. So the infrared spectrograph on Spitzer breaks up light just like a prism breaks up visible light. It does basically the same thing. So they took a spectrum of this object, and they've identified what all of these individual lines are. This big bite taken out is silicates, or beach sand. So what's going on is you have the bright thing embedded in its cocoon, and the light shining through it basically has these bites taken out of it that we're seeing, and that's telling us what the stuff around it is made out of. So we're seeing water ice and methyl alcohol and methane and carbon dioxide ice. So it's pretty darn cold around this object. Now, this is another spectrum that they released at the same time. This completely unremarkable galaxy here turns out to be an AGN, an active galactic nucleus. It's 3.2 billion light years away. Turns out to be one of the most luminous galaxies in the universe. Most of its energy is coming out in the infrared. So they got the spectrum in only 15 minutes of observing time, which is really quite remarkable. You can see lots and lots of structure in here, including silicates and water ice, just like you see in the object that's closer by, the previous spectrum. So one of the reasons that they released this image is because it is 3.2 billion light years away, and yet you see hydrocarbons in the spectrum. And they thought philosophically it was kind of neat that when the light from this object was emitted was about the same time that life was emerging here on Earth. There are hydrocarbons there and hydrocarbons here. So they thought that was kind of a neat thing to think about. I think that's everything that I remembered. Now, this is our very newest image. It was just released on Monday, so hopefully you haven't seen this one yet. This is Henneis 206, or HE 206. It's actually in the Large Magellanic Cloud, which is a satellite galaxy to our own. It's 163,000 light years away. The thing that makes the Large Magellanic Cloud kind of interesting is it has much less metals than the stuff in our solar neighborhood. Now, when an astrophysicist says metals, pretty much they mean anything other than hydrogen and helium. Okay, we don't mean foil wrap, you know. We mean lithium, beryllium, boron, everything, okay? So it turns out that this has just a fraction of the metals found locally. And because of the way that we understand star formation right now, we are pretty sure that having a lot of metals is crucial to being able to form stars in the first place. It's particularly to form planets. So studying this galaxy gives us insight into how really some of the first stars might have formed on the edge of the universe. So this here is a composite with IRAC and MIPS data. Here we have visible data, IRAC data, and MIPS data here. So it turns out there are actually two supernova remnants hidden in here. There's one here that you really can't see at all in the infrared. And then there's a big one, you can sort of see the shape of it here. It's a big bubble. So there's a supernova pushing the gas and dust around and triggering star formation in the cloud. Let me see if I can make it go again, just in case you blinked, because it's only a 16-second movie. Supernova pushes the gas and dust around and triggers star formation. So it's the death of one star, but the birth of many others. So that is what we think is going on here. What we're seeing, the bright stars that we're seeing in the infrared here, are the ones that were triggered to form by the death of another star in this cluster. So here's just another cartoon of it. Here's the supernova explosion, and the shock wave compresses the clouds, and you end up with stars forming in the wake of the shock wave. So moving out a little bit further, here's M81, which is, of course, an Ursa Major. It's 12 million light years away. This image is about a moon size across. And the thing that we think makes this image really cool is that you can actually pull apart the constituents of the galaxy by looking at different wavelengths. We thought that people would really like the IC 1396 image, but it turns out this one is really very popular. Here's another way of looking at it. Here's a little visible light. Here's 24 microns, 8 microns, and 3.6 microns. Look how smooth the blue 3.6 micron is and how clumpy the 24 micron is. It's because here at 3.6 micron, you're looking at the gas distribution, and here you're looking at dusty clumps that are star-forming regions in the galaxy. So when you combine it, you can actually see the blue stuff is very, very smooth, but you got really, really clumpy red stuff in the arms. You can see the arms going in almost all the way to the core. So the arms are actually density waves, so that's why they're compressing the gas and dust and triggering star formation. The galaxy, as you look at it on the sky, is about the same width as the moon. Okay? It's half a degree across. I don't truly mean that the galaxy is the same physical size as the moon, right? No, I mean that when you look at it with your eye, you're not integrating for a very long time, so you only see the brightest photons from the core. But when you are able to collect all the photons it emits for over a long period of time, you actually get to see the extended structure. You can see hints of that when you look at Andromeda with binoculars. Because with your eye, looking at the M31, you just see the fuzzy bit in the center, but when you have binoculars, you can collect more photons and you see it extending over a larger area. It's the same kind of thing here. This is M81, and you're going to look with your infrared eye. So that was M81. This is just an example, again, of M81, how the resolution changes as you move to longer wavelengths. So you go from 24, 70, and 160 microns. You can see that the resolution seems to get much, much, much worse. In terms of previous abilities to look at 160 microns, this is revolutionary. But it doesn't look very good compared to Hubble. So this is what keeps us up at night. This is what you have to do in order to get the MIPS observations all at the same resolution. You have to smear them out. So now you can fairly compare and say, okay, what's bright at 160, what's bright at 70, what's bright at 24, and try to learn what you can from the different characteristics. Okay, we try to aim for releasing a new image every couple of weeks. We hope for a tiny break in the Mars coverage occasionally. Like any NASA mission, you own the data too, because you are a taxpayer, you own the data. So I encourage you to go take a look. Our main archive opens in May 2004. Unusually for this mission, we actually have some projects that release their data right away. So usually the way that it works is that astronomers get their data, get to think about it for a year, and then it goes public. But it turns out that with this mission, because we're cryogen limited, because we have such a short lifetime, we have some projects that are designed to get the data out very, very quickly so that other astronomers can do follow-up observations. We have something called the First Look Survey, which was the very first thing that we did when we basically popped off the lens cap and started nominal operations. There's a little bit of a sampler out now. The rest of it comes out in May. This is a very technical slide that summarizes the First Look Survey. The bottom line is that there's three components. There's extragalactic, galactic, and ecliptic. We're looking for asteroids. Some of the data is out there now, but let me warn you, this is not sugar-coated. These are not GIFs and JPEGs. These are FITS images. These are real, honest-to-God astronomical data in all of their ugly glory with pages of caveats because it's very early data. But I do encourage you to go take a look because it is kind of cool to see the actual data. The reason we released some of these images early is because professional astronomers were writing proposals for observing time that were due in the middle of February. So that's why they needed to see some of the early data. And just very, very quickly, I saw some really sophisticated pictures up earlier. If you guys can do V equals 22 magnitude asteroids, we can use your help following up some of the asteroids that we found. So just in quick summary, so those of you that need to leave can, hopefully, if nothing else, you've learned about light beyond the visible. The world looks very, very different in the infrared. Spitzer studies the old, the cold, and the dirty, which means we're studying distant galaxies, star formation everywhere, dust everywhere, from comets to galaxies. We have lots of cool images with more coming soon, and you too can access Spitzer data. Okay? Thanks very much.
Thank you, Dr. Rebull, for a very interesting presentation on our newest great observatory. I'm sure there will be many unexpected discoveries made by the Spitzer over its observing lifetime. Talking of unexpected discoveries, have you heard the announcement by NASA of the newly discovered planetoid named Sedna? It is currently the most distant object ever discovered in the solar system. The Spitzer telescope played a strange part in the discovery. As you know, the Spitzer sees in infrared light. Well, it was tasked with seeing how much heat was being radiated from this very cold planet. The thing is, it didn't see anything at all, and that fact was used to establish an upper limit to the size of this new object to approximately 1,100 miles. Sedna is likely to be just one of the many large and distant objects that remain to be discovered. Keep your eye on the news for further information. One of OCA's functions, as well as this TV program's main function, is to bring the fun and wonder of the night sky to the general public. If you don't have a telescope, or you don't know exactly how to start, but you'd like to see some of these nighttime wonders yourself, please access our website at www.ocastronomers.org for upcoming outreach events throughout Orange County. You'll find the OCA membership friendly and very eager to share the sky with you. Our website has additional information about many other activities the club has to offer. Additionally, this coming April 24th is Astronomy Day throughout the country. Many astronomical organizations are running special events that day, and you can see what activities we are offering that day by accessing our website. If you're interested in attending one of our star parties at Black Star Canyon or ANZA, please send an email to lookuptonight@ocastronomers.org. Well, thank you for joining us this evening. We're looking forward to seeing you again at our April meeting, which has been rescheduled from April 9th to April 16th. Or tune in to our next show. Until next time, get outside and look up tonight.